And I'll start with the announcement that's about what's happening this week. I've mentioned it before. I'll go on and get it said now. This is Cougar Connection Week, okay? And there's activities on both campuses today, tomorrow, and Wednesday. On Thursday, they're mostly on the Birmingham campus, but we got it. And some things will actually spill over to next week as well, I think. Okay, so here on this campus today we're celebrating Constitution Day. I'm not sure when that is. I don't remember from Sesame Street, when the Constitution was written, but I was too old for Sesame Street, by the way. So anyway, but it's in the faculty staff dining room, and that begins at 12 noon and goes to 1 o'clock. So if you can go, it should be quite good. The faculty staff dining room is just this side of the cafeteria, okay? And that should be a pretty good presentation today. Now, on the Birmingham campus, all morning they've been having the Get On Board Volunteer Fair. So several organizations are set up over there, and here's DeMarcus. Here are a few of the ones that may be there. Big Brother, Big Sister, Ben Green Housing Authority, Bessemer Recreational Center, Faith Chapel, Girls Incorporated, Grace House, Hands on Birmingham, Humane Society, Metro Changers, Oaks on Parkwood, Operation Hope, Powership Network, and the Red Cross. Now, every time I read the Red Cross, I'm reminded, I'm pretty sure one of the Student Government Association guys in one of my other classes said that they're having a blood drive next week. They tried to schedule it for this week, couldn't get it, so that will be next week. So that's what we'll carry over today. But anyway, those are the outside organizations that you can check and see what they've got, see if they've got anything you'd like to volunteer with. But then also, they have the student organizations you may want to become a part of. That's in the proposition, should do that. The ambassadors, athletics, fine arts, honors college, PBL, that's Phi Beta Lambda, mostly a business type organization, I think, but they accept anybody. Scholars Bowl, Student Government Association, speech and drama, speech and debate, student support services, and STEM, which is science, technology, engineering, and math. And they, I think, will have tables on or information available on Birmingham today. Daniel is here. All right. Now, today, if you're going to the Birmingham campus, that goes until 1 o'clock today. The Get On Board Volunteer Fair. Tomorrow, things flip-flop. Okay? On this campus, they'll have the Get On Board Volunteer Fair, and that will be in the little courtyard that's down there outside the library where B building, the bottom floor of B, first floor of B building, and the library, that little courtyard down there. And it may spill over into the sidewalk coming around the library. That's where I'm guessing it is. It's down from where you come in the building here, the student activities entrance. You go down a set of stairs before you get to the building, and you'll see the courtyard down there. Okay, that's where I'm guessing it is. On the Birmingham campus tomorrow, they'll have the Constitution Day program, and that will be in Thelma Catlin Auditorium. That's in the library building, Building D, from 12 to 1. Now, Thelma Catlin Auditorium is there in the building, but it's not real easy to find. So just stop and ask anybody where Thelma Catlin. It's real short. It's right there. It's just not well documented. It's not well advertised that Thelma Catlin is there. They may have a few signs up, but it's easy to miss them. Okay. So, the things going on Wednesday are going to be after this class is over, so I'll wait till Wednesday to announce those. I'll do Wednesday and Thursday then. Any questions on that or anything that we've done so far? All right. Example 8 we did. We also did example 9. It wasn't shown on the slide set, but we did it. But right after example 9, there is a little blurb at the bottom talking about geometrically what you can interpret equations to be. Okay? And most of you have books. Not really. Okay. I'll try to do this. To me, this doesn't quite look right, but they indicate that it is. Seems like there'd have to be a little more curvature in this line, but they are not showing it. It's referring to example 9. So let me write down example 9 again. Let me get my pen back. Okay. Example 9 was the integral from 1 to 5 of x over the square root of 2x minus 1, and then we had the dx up here. Okay. Now, what they show, and I find almost hard to believe, that this is the graph of that function. Okay? Going from 1, 1, I think you could verify that. Yeah, because 2 times 1 is 2 minus 1 is 1, square root of 1 is 1, so 1 over 1 is 1. So yeah, that's the first point. Up to the last point, which would be, and do the same up here. Okay, 2, 3, 4, 5. At 5, this would be 2 times 5 is 10, minus 1 is 9, square root of 9 is 3, so that would be 5/3. 1, 2, so it's right here. 5 5/3. That's really ugly, isn't it? Okay. Okay. All right, 5 5/3. And they show that as being basically a straight line. I, for the life of me, cannot see how that turns out being a linear function. But what that integral is asking is the area under this curve. Okay? Now, when we did the substitution, and you'll have to go back and look at your notes, that gave you f of u and I'm not going to redo this, but that gave us from 1 to 3 of u squared plus 1 over 2 du. Okay? Now that's obviously a quadratic function, and that graph I can buy. That goes from 1 to 3. Okay? And it goes from 1, 1. Again, if you look at that, 1 squared is 1, plus 1 is 2, 2 over 2 is 1. So it goes from 1, 1 to up to 5. All right, 3, 5. Because you put a 3 in there, 3 squared is 3 plus 1 is 3 squared is 9 plus 1 is 10, divided by 2 is, and that's a parabolic equation. And they say that this area under here is the same as that area there. you can't dispute it, but it looks like it's the same, and sure enough it is. And that's what your substitution is, going from one that is very difficult to, in fact, almost impossible to integrate the way it is. So that's really easy. And it actually looks like this would be easier. If that is a straight line, that would be pretty straightforward. I don't think it is. But that is a parabola there, and that's not hard to do. This one, if it has some curvature, is very slight. But I haven't checked it out to see. But that's all the bottom of that page was doing. Okay? No, not quite all. Here's another one they're showing us. So I'm going to see if I can find a little bit more room to work. So let's, yeah. Ooh, that's not bad there. Okay, I'm going to use this. This is not an example, but it's underneath example 9 in the text. Okay? Here is the integral. 0 to 1. Here's the integrand. X squared times 1 minus x squared, no, 1 minus x to the half power dx. Okay. Now, anyone want to tackle that as is? I think and hope not. That's not going to be an easy one to do, the way it's written.
First, you have to give it power rule. You have to use string rule.
Okay. I heard you mention the power rule. That would work with this fine, or it would work with this fine, but the combination of them not going to work too well. Now, what you might be tempted to do is say, can you distribute this in? No, you can't. This is a square root here, so yeah, that's a lot worse to try to distribute in. You have to write this as x to the 4th to the 1/2 power, which would be x squared, and then you can distribute that in, but that's really messy. Okay, so no, you can't as is. So what might we try? It's the title of this section. What's that?
Section is integration.
Second?
Integration.
Integration, yeah.
Yes.
How? What technique? Okay. You got tired on the basketball court and they sent someone else in? Substitute. All right. It's substitution method. All right. All right. Integration by substitution, 4.5. All right. Now, what might you choose for your substitution? What's my little rule?
1 minus 6.
Yes, it would be 1 minus x. The innermost part of the most complicated part of your integrand.
So 1 minus.
Yeah, because 1 minus x is raised to the 1/2 power. Let's use that as our u. So let u equal 1 minus x. Next step, then du is equal to it's really not that hard. Root of a 1.
Dx.
Okay, it's going to be a dx with something in front of it.
Oh, negative?
A negative dx. Okay, you saw my little circle going there. Okay, a negative dx. So, to rearrange that then implies that dx is equal to minus du. Just multiplying and dividing by minus 1. Okay? So, we still got that pesky x squared in front, right? We need to do something with that. Well, here's what we do. we go up here and solve for x. Add x to both sides and subtract u from both sides. And that gives us x equal 1 minus u. Yeah, you just flip, move them across the minus, the equal sign. Okay? Well then, x squared is what? Help me. If x is 1 minus u, what would your x squared be? 1 minus what?
U squared.
Okay, there is a u squared there, but it's not after a minus sign. Okay, you remember the shortcut? Okay.
Yeah, I can remember the shortcut.
Okay, shortcut is square the first, twice the product, square the last.
Oh.
So that's always going to be a plus squared. Okay, this is, now, if you don't remember the shortcut, go on and do it out. Square. 1 minus u squared is 1 minus u times 1 minus u. That's what it means to square something. Multiply it by itself. Then you FOIL it. 1 minus u minus 2u plus u squared. Yeah. Okay. That gives you your same. Okay. So that's that. Now, with that in mind, let's go back to our integral here. That will be the integral. Now we're not quite ready to do the limits yet. Maybe we are. Want to do the limits now or put down the integrand first? Huh?
Put down the integrand.
Integrand, okay. Your x squared is this thing right here. So 1 minus 2u plus u squared. That's what x squared is. The 1 minus x is u. And that u is raised to the 1/2 power. And then your dx is minus du. So put the minus in front and the du out here. Okay. Everybody agree that I've translated my integral, right? But I don't have my limits yet. So here's where we go to the limits, where we started from. Let u equal 1 minus x. With x is 0, u is 1 minus 0 is 1. Okay? So this will be 1. Okay? But where x is 1, the dx is x is 1, what would your u be? 0. Okay. Well, that's not very nice, is it? Because we like to have the small number on the bottom and the larger one on top. So how can we flip that? Yeah, make it positive. So this is the same as the integral from 0 to 1. Lose the minus sign here because that negates it to do that. And now let's go on and multiply through our integrand while we're doing. What would that be? Distribute this across each term here. U to the 1/2 minus 2u to the 3/2 and second plus 5/2. Perfect. du. Okay. Now, can we integrate that? Antiderivative of u to the 1/2. Antiderivative of u to the 1/2.
Two-thirds u.
Okay, 2/3 u to the 3 has power. Perfect. Minus 2 times
5 has.
u to the 5 has power times 2/5. Okay? You already had a 2 there, so I'll put 2 times 2. Plus
Plus 2 over 7u.
2 over 7 times u to the 7 has power. We'll evaluate that from 0 to 1. Okay? And these are both so easy, I want to do them. No, okay. All right. When you put u in there, u to the 3, when you put 1 in for u, 1 to any power is 1. Okay? So that's just going to be a 2/3 minus 4/5, right? Plus 2/7. That's it, just your coefficients. Minus zeros in there. 0 minus 0 plus 0. Not going to add a thing. So they were both so easy, I did them. Okay, sorry, I shouldn't have. But do you see why they come out that way? All right, now, the calculus was the easy part. Now the fractions, getting least common denominator, that's the hard part, isn't it? What's the least common denominator between 3, 5, and 7? And
35.
here's Vince, right? All right.
Least common denominator is 35. I believe.
You said 35?
Yes.
3 won't go into 35, will it?
Is it 30? Yeah. Sorry.
These are all prime numbers, by the way.
What was that?
Huh?
Yeah, because it started that. Yeah. Sorry.
Yeah.
105.
Whatever 3 times 35 is, that sounds like 105. 105 minus 105 plus 105. Okay, those are our denominators. How many times will 3 go into 105? Obviously, 35 times, right? Times 2 is 70, right? And 5 will go into 105 21 times. And 21 times of minus 4 is minus 84, right? And 7 will go into 105 15 times, so that's going to be a plus 30. Buy that? So that comes out being 100 over 105 minus 84, so I think that's right around 16 over 105. Let's see if that's what they got. Oh my goodness, look at that. They got it right too. It's right at the bottom of page 303. Y'all see it? Understand it? Agree with it? All right with it? Have a question about it? I'll be glad to try to field any questions. Any? Okay. All right, now we're finally ready for integration of even and odd functions. Okay? Now, even with a change of variables, integration can be difficult. Oh, why did they say a statement like that? Oh, okay. Occasionally, you can simplify the evaluation of a definite integral over an interval that is symmetric about the y-axis or about the origin by recognizing the integrand to be an even or an odd function. So, if you happen to be integrating this thing from minus a to a, and you see, well, this is an even function itself, and integrate from minus a to a is the same as to double the integral from 0 to a. And guess what? This is a lot easier to evaluate that at 0 than it is at minus a. and it's just twice the size of that. So it'd be 2 times the integral between 0 and a. And you get the same value. Okay. However, if it's an odd function, and you're going from minus a to a, anyone want to hazard a guess about what that integral is? Zero. Why? This part's positive, that part's negative. They're exactly the same. So the areas are exactly the same size, but one's positive and one's negative. Adds to 0. Okay. So that works out. That's really easy. Probably not very satisfying, but this is pretty easy too. Even functions, you can double if they're symmetric in their evaluation. Now, if it's going from B to A or A to B, and they're not on either side, yeah, you can't do anything. But if they're minus A to A, and it's even function, just do 0 to A and double it. If it's an odd function, going from minus A to A, 0, it's done. Okay. So here is the verbiage that says that. Let F be integrable on a closed interval from minus A to A. Whatever you're doing on the left-hand side, you go just as far on the right-hand side. If F is an even function, then the integral from minus A to A of f of x dx is exactly twice the integral from 0 to A of f of x dx. You only have to do one side and double it. Okay? But if f is an odd function, you don't even have to do that. It's 0, because the minus a part is going to either be positive or negative area. The plus a part is going to be the opposite, negative or positive area. They're going to add to 0. Because you're symmetric about the origin. Whatever an odd function, if it's going up on one side, it's going down on the other. It's going down on one side, it's going up on the other. And exactly the same pattern. And if you're going from minus a to A, the total area is going to be zilch, 0, none, nada, nothing. Okay, so that's what we've got. Let's do an integral here. Okay, evaluate this integral. Integral from minus pi to pi, minus pi halves to pi halves of sine cubed x cosine x plus sine x cosine x dx. Now, I don't know how much your analysis is, but what kind of function is sine x to begin with? Sine x. Anybody? Huh? I'm sorry?
This one was kind of sine. Yeah, I know it's treated on the function and the can't know the word for it, but the other thing is cosine. Sine x equals cosine x. Right? I think that's what
Yeah. It is a trig function, but in terms of even and oddness, what is sine? Odd. It's an odd function. And cubing is a odd function. Okay. Cosine, however, is an even function. So you've taken an odd function, you've done an odd operation with it, so that's odd, and multiply odd times the even, and what do you get? Odd. Yeah. Now, I don't know if you think in those terms, but I think it pluses and minuses, you know, well, plus being even and minus being odds, that's going to be odd. How about sine x cosine x? Odd times even is odd. So that looks like this is an odd function. And what's the integral from those two? Minus pi halves to pi halves of odd functions.
0.
0. That's what my gut tells me, besides that it's hungry, but let's actually do the math and see what we get. In the first part there, how could we do that?
I want to see sine x cosine x.
No, just sine x.
Sine.
The innermost part of the most complicated part of that first term. Sine cubed is the most complicated part, sine's the innermost part. Let u equal sine x, then you finish it. So du is equal to cosine x dx. And there we have a cosine x dx. In fact, looking at it this way, let's rewrite this whole thing as the integral from minus pi halves to pi halves of sine cubed x plus sine x times cosine x dx. Okay? Is that right? What I did is factor out a cosine x, right, from both terms, leaving just sine cubed x plus sine x times cosine x dx. That's going to be our du. It's going to be the du for the second part too, isn't it? Let u be sine x, du would be cosine x dx, so that would be it. So what we would have then is what? The integral from, I won't put limits there yet, if u is sine x, sine cubed x is u cubed plus plus u, and then du. Okay? Now, let's deal with our limits. When x is equal to minus pi halves, what is sine of minus pi halves? Negative 1.
Yeah, that was negative 1.
Right. And sine of pi halves is? 1. Okay. So your u's are going from minus 1 to 1. All right. Can we do that integration? Pretty easy, isn't it? What's the first one?
Negative 2.
Okay. All right. Done in a hurry. What is the antiderivative of u cubed?
U to the 4 over 4.
4.
Plus u squared over 2.
Okay. Evaluate that from minus 1 to 1. Okay. I can do the 1 part. That would be 1/4 plus 1/2. Agreed? Minus. Now do the minus 1 part. Minus 1 to the 4th power is? Okay, okay. It's 1/4, and we got the minus sign, so that would be a minus 1/4. Because when you do the minus to the 4th, that becomes positive. Yeah, okay. And then this would be a minus 1/2, and that adds to 0. Just like we suspected up here. And we didn't have to do all that if you recognize that was indeed an odd function. But when you got it down here, you knew it was an odd function, right? No more speculation with, even an oddness. That is obviously an odd function, one from the same thing, 0. right off the top, 0. Okay. Now, what they did a little test for an odd function. And what's the test for an odd function? Put in a minus x. So sine cubed of a negative x times cosine of a negative x plus sine of a negative x times cosine of a negative x. Okay? Well, sine of a negative x is going to be minus sine x. You cube that, you still get minus sine cubed x. Okay? And cosine of a negative x is cosine of x, so that's an even function. So that'll be cosine x. And this is going to be sine of a minus x is minus sine of x. It's an odd function, remember? So that's going to be a minus sine x. But cosine of negative x is cosine x. So it's cosine x. Well, this thing is exactly the opposite of this thing. So this is equal to minus, or this thing is equal to minus that thing. So odd function. Ding, ding, ding. Perfect attendance again today. Way to go. All right. Excellent. All right. What's that?
As a solid ruling your flow, but I'm not seeing how that's obviously an odd function above when it being evaluated from negative 1 to 1, the UQ plus U.
How's that odd?
Yes.
Okay. You can either plug in your minus x's there and see, and as long as you put a minus u, this is the minus u cubed minus u, which is exactly the opposite of that function. Okay, that makes it odd. The other thing is, what's your exponent here? Which is odd. Exponent here, which is odd. So it's an odd function. Polynomials, that works with. You can't always say that's true for other kinds of functions. Maybe for some, but not always for others. Okay. But anyway, it comes out 0. That finishes, finally, 4.5. Homework exercises here, and I've announced most of these before. Any of the odds, either 5 or 7, both are at Calc Chat, 5's at Calc View. Any of the odds 9 through 29, they're all at Calc Chat, 15's at Calc View. Any either 31 or 33 or both, they're both at Calc Chat, 31's at Calc View. Do 35. We didn't do one like that in class, but if you want to look at it, you can, and that's at Calc Chat. That might be helpful to you. 37 also would be at Calc Chat. Okay? And I think that's another, well, no, it's a different issue. Any of the odds 39 to 47, they're all at Calc Chat. 45's at Calc View. Any of the odds 49, either 49 or 51, they're both at Calc Chat. 49's at Calc View. Any of the odds 53, the 59, they're all at Calc Chat. 53's at Calc View. Any of the odds 61 to 67, they're all at Calc Chat. 65's at Calc View. Either 69 or 71, they're both at Calc Chat. 69's at Calc View. Either 73 or 75, they're both at Calc Chat. 73's at Calc View. Do 77. It has 4 parts to it. It should all be at Calc Chat. Then, the new thing today, well, the last ones were even and odd too, sorry. That started with 73. But 79's and even odd, so it should be at Calc Chat as well. Now, why do I have this here? I guess there's more paper. All right. You can look at 81 if you'd like. It should be at Calc Chat. I don't know if it is or not. 83 is a good one, especially if you're going into business and you need to depreciate stuff. That's a good problem. 83, 85. I would say any of the odds, 83 through, wow, 91. You choose the ones, well, let's see. Let me make it 83 through 89. Okay? Choose whichever of those are of the greatest interest to you that you want to do. All those should be at Calc Chat. Okay? 89 is a probability problem. 91 is a probability problem. You can do that if you'd like. There's some true false, any of the odds 93 to 97. You can do those. 91, is rewriting an integral. I think you can do that. 101 is a proof. If you're interested in that, go for it. And that finishes what we're going to do in Chapter 4. And if my memory's right, we started in 4.3 or 4.2. Was it 4.2? 4.2? Okay. So 4.2 to 4.5. Was going to do the test on that until I realized there's a little bit in Chapter 5 that you might want. But let's look at some review exercises. And again, these are at Calc Chat. And I can't remember where 4.1 ended and the others began. But you can do any of the odd numbers of any of those that would be in 4.2 to 4.5. Okay? I'll just leave it like that. Problem solving is on page 311. If you find that of interest, you can certainly look at that. What I wanted to do was do a little bit in Chapter 5 because we're going to be using this later. So let me get out of Chapter 4 and into Chapter 5. I'm just going to do this pretty quickly because this is stuff you just need to know bits about. I won't go into gory detail on it. Probably a little bit is too gory for you, but we're going to be using this a lot in the future, so I think it's worthwhile to do now. Okay. These are logarithmic, exponential, and other transcendental functions. I think I told you before that there were two texts. I didn't realize that we were not getting the one that said early transcendentals, but we weren't, okay? So logarithmic, exponential, and other transcendental functions. 5.1 is a natural logarithm, and we're going to be dealing with differentiation of it. Natural logarithm differentiated. We'll develop and use properties for the natural logarithmic function. Understand the definition of the number e, okay, and find derivatives of the functions involving natural logarithmic functions. So, what is the natural logarithmic function? The general power rule, as we know, is the integral of x to the n dx. The antiderivative of this, we usually increase that by 1, right? And then divide by that same number. So it would be x to the n plus 1 over n plus 1. But, and then we add a c to it if it's an indefinite integral. What's the only possible wrong with that picture? What can n never be? Negative 1, to make the denominator 0. Yeah, negative 1. So this won't work for n equal negative 1. Okay? It does not apply because you can't divide by negative 1. Consequently, we have not found the antiderivative of this function, x to the minus 1. We just don't know it. It's not a power function. It is a power function, but we can't use it for it. In this section, we use the second fundamental theorem of calculus to define such a function. And we're not going through this in gory terms. It is neither algebraic nor trigonometric, but it falls in a new class of functions called logarithmic functions. This particular function is the natural logarithmic function. Basically, this is all we're going to do. Rather than go into gory detail about it, we're just going to define it this Definition of a natural logarithmic function. Natural logarithmic function is defined as log n, that's Ln. Most of the time, if you write log for log, you need a base after it. You know, base 10, base 2, base 12, whatever base. The natural logarithmic function, we just write Ln. Okay? So natural log of x is the integral from 1 to x of 1 over t dt. That's just its definition. Okay? Is the door locked? Is the door locked on the outside? Is it? If you pull on it too hard, it jams a little bit. But was it locked? What's that?
It wasn't locked when I twisted.
Oh. Okay, but it's not locked now, is that right? Yeah. I've got a key. I don't have as many as I have one for that, but plus the others I don't have. Okay. Now, this isn't how I usually think of the natural log function. It's definitely true. This is the definition. The log of x is the integral of from 1 to x, 1 over x, 1 over t dt. As long as x is greater than 0. X is greater than 0. Okay? Now that seems a little bizarre. You would almost think it had to be greater than 1, but it doesn't. It could be greater than 0. Okay? But it has to be greater than it. It can't ever be equal to 0. The domain of the natural logarithmic function is a set of all positive real numbers. Domain of the natural logarithmic function is all positive real numbers. Okay? Not 0. Okay? Not non-negative numbers. Positive real numbers. And that's all. You can't take the log of 0. You can't take the log of any negative number. Ever. Okay? Including -1, but not limited to -1. You can't take the log of any negative number or 0. Okay. From that definition, you can see that log x is positive for x greater than 1 and less than negative for x between 0 and 1. Okay? Now, I don't know if you saw that right off the top or not, but you see if x is, it can't be 0, but anything greater than 0 up to 1, this is going to be a negative value here, right? Because 1 to 0.5 or 1 to 0.9 or 1 to 0.1 or something. This is bigger to smaller, that's going to be a negative value. Okay? But anything greater than 1, this is going to be a positive value. 1.7, 8, 15, 45,000. You know, anything there, those are going to be positive numbers. Okay? When x equal 1, this happens to be 0. Okay? X can be 1, then the log x is 0. So there's an important feature. Log of 1 is 0. Okay. Okay. Moreover, log of 1 is 0, because the upper and lower limits would be equal when that's 0. Now, trying to see what they're doing here. Oh yeah, got it. Anything greater than 1, log of 1 is 0, because you got the area of a very thin line, 0. That has no area. Okay, so anything greater than 1, you're doing the integral from 1 to x. X is greater than 1. That's going to be a positive area here. Okay. However, if x is less than 1, then this is the positive area, but this would be, the area here would be the area from t equal x to 1, but this is t equal 1 to x. So to get x1, you have to flip them, and that becomes negative. So that's why these areas are negative. That's a positive area, but you're doing, this is from x to 1, this is from 1 to x. So that makes it negative. And again, to me, this is an easy way to remember this. I'll show you the easy way in a little bit, okay? I have to really think about it and convince myself, oh yeah, I see what they're talking about. Okay. There's easier ways. Okay. To sketch a graph of log x, y is equal to log x, you can think of the natural logarithm as the antiderivative given by the equation. And again, this is not how I remember, but it works. Okay. When x is a very small positive number, then this is going to be a huge derivative, almost straight up, okay? When x is 1, that is 1, slope of 1. And when x is anything greater than 1, the slope is going to be less than 1, so it's going to be pulling it down, but it never flattens out. It's always going up. And this, again, is called a computer-generated graph, a slope field. And since I don't have a computer to generate them, I have to do them myself, and they're a pain in the neck to do. But I have a lot of writing to do, calculate. The graph of y is equal to 1 over x is the solution that passes through the point 1, 0. That's your function. Anything between 0 and 1, not 0, but anything between 0 and 1, those are negative values. Anything at 1, it's equal to 0, and anything beyond that is positive. Okay. That's your log x function. That's how it looks. To me, this is not the easy way to remember it. Okay. The next theorem lists some of the basic properties of the natural logarithmic function. And these are pretty important. Okay? Properties of the natural logarithmic function. Natural logarithmic function has the following property. Boy, they've said that 3 times now. The domain is from 0, but not counting 0, to positive infinity. Can never be 0, can never be negative. Okay? The range, though, is from negative infinity to positive infinity. It goes all the way. That function never levels off. It's always increasing. Okay? It's a continuous, increasing, one-to-one function within that domain. Okay? And the graph is concave down, as we saw. Concave down. Okay? Always increasing, but concave down. Meaning the rate of increase is decreasing all the time. Yes?
Maybe concave down. I know this is a little technical, but how about that this continuously, if it's going to continuously increase, why would it concave down? It's not really.
Okay. It doesn't cup all the way over, but it is always, the first derivative is decreasing. So it's extraordinarily positive here, a little less positive here, a little less positive there, a little less positive there. So the first derivative is always decreasing, which means it's concave down. Okay? It doesn't ever turn and go down, but it is concave down. Concave up would be like this, even though it never, went back up again. That would be like this. So this is concave down. Okay. Now, again, this is not how I remember all these features of it. I'll get to that in a little bit. All right, concave down. Using the definition of natural logarithmic function, you will improve several important properties involving operations with natural logarithms. If you already are familiar with logarithms, you'll recognize these properties as characteristics of all logarithms. So if A and B are both positive numbers, guess what? They can't be negative. You can't take the log of a negative number. You can't take the log of 0, so they have to be positive numbers, not non-negative, positive. N is rational, okay? Then the following properties are true. Okay, we've already said that. The log of 1 is always 0. 1, 0 is always on that. Log of 1 is always 0. Okay? The log of a product is the sum of the logs. Remember that one? Log of a product is the sum of the logs. Not product of the log, the sum of the logs. Okay? Number 3, the log of a power is the exponent times the log of the base. Exponent, in other words, take the exponent, bring it in front. exponent times the log of the base. Okay? And the log of a quotient is the difference in their logs. Log of A minus log of B. Okay. Now, log of 1 is equal to 0. I already talked about this. Notice what this is doing. It's taking a multiplication problem and reducing it to an addition problem. This is taking an exponential problem and making it a multiplication. This is taking division and making it a subtraction. And here's how I think of what's going on here. Your base operations are adding and subtracting. The easiest, simplest, the most fundamental operations in algebra are adding and subtracting. Multiplication and division are the next level up. They're a little more complicated, but just not much. Next above that is powers and roots. Okay? So, what a log does is take the multiplication and drops it down to an addition. It takes a power and drops it down to a multiplication. It takes a division and drops it down to a subtraction. And that's really what it's doing.
So it never does anything to roots.
What's that?
So it never does anything to roots.
To the root. I mean, the base.
Yeah.
Yeah. Well, it uses it. You know, here, everywhere it uses it, but it doesn't. Yeah, it doesn't. In a sense, affected it. I mean, you evaluate it using the log. Now, I know all of you are too young to remember this device, but you may have studied in a history class. Does anyone know what a slide rule is?
That's a little thing that you like move
The centerpiece.
Yeah.
Yeah, that's what the slide rule was. And what it was, before they had calculators, and guess what? There was a time before calculators, okay? None of you remember a time before calculators, but there was one, believe me. I would live through it, okay?
Is it known by another name like an abacus or something like that? Or
What's that?
is it known by another name like an abacus, or I'm trying to think of it.
Like a, what is
Abacus.
agabus or something like that. Yeah, that was what the Chinese used with beads and stuff. It may have had some of the same features, but a slide rule was this. It was basically a log scale and another log scale. And the middle thing slid. Okay? And back before they had calculators, when you're dealing with especially really big numbers, okay, you could write it or think of it in scientific notation, okay, 7.35 times 10 to the 18th or whatever. Huge number. But just deal with the first part. 7.85, find that on the upper scale, as close as you can get. You might have to approximate that last digit to 5. You can do 7.85, something in between 8 and 9, 8.5, and move your little window thing there. Slide the slide part over to stop right there. Multiply that by 8.97 times 10 to the minus 6. Doesn't matter about the other part. 8.97, you go that up here. Since you're multiplying, you're adding the logarithms. That's exactly what the slide rule did. If you're dividing, you're subtracting the logarithms. Okay? And if you're raising to a power, you take the power and multiply it by the logarithm. Okay? It was a device that gave you a decent approximation of multiplying and dividing of big numbers. Okay? That's what a slide rule was doing. Okay? Before you had calculators, that's about the best you could do. Okay? Now, by the way, I thought it was going to show it on the slide set. It doesn't. John Napier is featured on page 314 at the beginning of this section. He's the guy who first came up with, but I think he did base 10 logarithms, I think. But he coined the Greek word. Logos is ratio, which I thought was a word, okay? And arithmos, which is number, logarithmic, okay? So he put those two together. Back then they wrote everything in Latin, so they're a strange kind of thing. A description of the marvelous rule of logarithms. He didn't introduce the natural logarithms. Although he didn't, it's often called the Napierian logarithm, which I don't know why, because he didn't introduce that. They came up with that later. I bet you that was Euler later, but I don't know for sure. But Napier came up with that. Scottish, I think he was actually, they say he was a mathematician. I think he was actually a pastor too, but he was well educated, and he came up with this way to make numbering easier. All right, so the log of 9/10 or 10/9 is simply the log of 10 minus the log of 9. Now, you have to use your calculators to come up with those, but it's just a difference. So the log of a quotient is the difference of the logs. Okay, property 4. But you have to use your calculators anyway, so you could just do log of 10 over 9. It doesn't matter. Okay. But that's obviously going to be a positive number, right? Because log 10 is greater than log 9. Logs are always increasing functions. Okay. Now, how about this one? First thing you do is rewrite it as 3x plus 2 to the 1/2 power. Now you use the rule of logarithms, 1/2 times the log of 3x plus 2. And that's what they're going to show next. They're doing too much of this for you. 1/2 times the log of 3x plus 2. That was property number 3. So it does make things a lot easier in some senses. Okay. Log of 6x plus 5 divided by 5 is log of 6x minus log of 5.
So
But
dividing, you subtract.
yeah, dividing, you subtract the logarithm. Okay, but then multiplying, you add them. So this is log of 6 plus log of x minus the log of 5. So log 6 minus log 5 is whatever that is, plus the log of x. So you can change things and make them, once you know what the logs are, which you have to use a calculator for anyway, this makes for some easier mathematics, you might say. All right, how about something like that? Well, just do it a step at a time. How do you eat a 5,000-pound elephant? One bite at a time. Okay, so let's take the log of a quotient is the difference of the log. Log of the numerator minus the log of the denominator, right? Well, that numerator is the power, so that's 2 times the log of x squared plus 3, right? And here is a quotient, a product. So that's minus the log of x minus the log of the cube root of x squared plus 1. Okay? So let's get those steps on there. This is 2 times the log of this minus the log of x, and this is in bracket here, plus the log of this thing to the 1/3. Always write your radicals as exponentials. Okay? Once you got that, then that's 1/3 the log of this again. Okay? So do that. Ooh, they didn't do it yet. They distributed first. They distributed the minus here and there. I would have just done it all through the first step. They distributed that, and then they'll get this stayed the same, that stayed the same. This becomes 1/3 the log of this. But here you have 2 times the log of this minus a third. That would be what? 5/3 the log of this. So you just simplified it a little bit. Oh, they didn't show it. They left it there. But because those are the same bases there, you can make this. Oops, let me get my pen back. Okay. But warning, warning, warning. If you have a log of a product, a quotient, or a power, you can simplify. If you have the log of a sum or a difference, there's no place you can go. You're at the bottom rung, there's no place. You can't simplify that. You can't do this as log of something x squared. No, you just can't do it. You can simplify log a product, a quotient, or a power, but you can't simplify a sum or a difference. Not with a logarithm. So don't ever try it. Don't ever try it. You're at the bottom rung, you can't go any lower. That's what the logs do for you. Now, this isn't any better than what they had, but it's just a lot. Oh, no, it isn't. Sorry. Wrong. Okay. I was thinking that was x squared plus 3 here, too, and it's not. That's x squared plus 1. No, nothing else you can do to simplify this one. That's as far as you can go. That surprised me, but sorry, I misread it. Okay, that's as far as you can go. All right, where were we? Here we are. What's that? Yeah, we're getting ready to do example 1, I think. In fact, that is example 1. Oh, yeah, we just did example 1. I'm sorry. Yeah, that's what we just did. Example 1. All right. The next thing they're going to show is that little diagram off to the side. When using the properties of logarithms to rewrite logarithmic functions, you must check to see whether the domain of the rewritten function is the same as the domain of the original. Okay? Here is f of x is equal log of x squared. It can be written like this. That's defined everywhere. No matter what x you have is, except x equals 0. X cannot equal 0, right? But it can be positive or negative. Okay? So your domain is all real numbers x except x equals 0. Can't take log of 0. Okay, but if then you change this to be 2 times the log of x, nope, these aren't good anymore. There your x's are only positive. Okay? So keep that in mind that when you do change that, you may be changing your domain as well. For instance, the domain of this is all real numbers except x equals 0. The domain of this one is only positive real numbers. So even though they say they're equivalent to each other, the domains are different, definitely different. Okay, just a little note. Now, the number e. What do you know about e? Anything?
It's like
2.7 blah, 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 blah. Like pi is 3.141 blah, 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 blah. E is the same way. It's an irrational number. Starts with 2.7. I don't remember the next digit. It seems like it's a 1. But yeah. And it goes, but it never repeats any pattern whatsoever. Okay? It's an irrational number. So that's what we know. You know why it's named E?
I'm sure it's some sort of Greek.
Not Greek. Euler. He was Swiss or German or something. He came up with it, so they either he named it E or someone named it after him. E. And we often call it the base of the natural number system. It's likely you've studied logarithms in algebra course. There, without benefit of calculus, you would have defined it as the base in terms of a base number. For example, common logarithms have a base of 10. That's what that stands for. The base of the natural logarithms, using the fact that natural logarithm function is continuous, 1 to 1 has a range from negative infinity to infinity. That's the number of e. Okay. Now, and this is not, I guess I've used it from the algebraic viewpoint. there must be a unique real number x such that the log of x is equal to 1. Not the log of 1 is equal, that's 0, but the log of x equal 1. That number is denoted by the letter E, can be shown as an irrational number, has the following decimal approximation. E is approximately 2.71, and then the digits, they look like they're going to repeat for a bit, 1828, 1828, but then they don't. Okay, that's just a little anomaly there that happens at the beginning. After that, there's never another repetition. And that only happens twice, but it doesn't happen again, so it's not a repeat. Okay. Now, this is the way they refer to E. It's that number, approximately 2.72 is what they say. That is where that is the number here that this area would be exactly 1. Okay. Strange way to look at it, but in fact, really strange. Okay. So the definition of E, the letter E, denotes the positive real number such that the log of E is equal to the integral from 1 to E, 1 over t dt, and that's equal to 1. Okay? And once you know that the log of E is equal to 1, you can use logarithmic properties to evaluate the natural logarithms of several other numbers. Okay? A lot of blah, blah, blah here. Okay? For example, by using this, log of E to the nth would be n times the log of E, but log of E is 1, so log of E to the nth is n. Okay? That same thing. All right? You can evaluate the log of E to the n for various values of n, and from the table you can get closer and closer to 1. Okay? So knock yourself out with that. I mean, it's just really. Second. Log of E is 1. Yes, log of E is 1, and E to the we'll get there in a little bit. I'll take something else. Yeah, the log of E is 1. The log of 1 is E. 1 is E to the 0th power. Log of E to the minus 1 is minus 1. So this very thing we saw here, this enables you to do that. And since E is fairly close to 3, 2.71, I always just square 3 or raise 3 to whatever power. This is fairly close to 1 over 9, 1/9, right? Yeah, 1 over E. Yeah, and no, I'm sorry, 1. If E is close to 3, this would be close to 1/3. Okay, and that is fairly close. This is 1/9. That would be close to 1/27, or sort of close to 1/30. But if you think about this, there's half, that would be pretty close to 1/3, 1/9. Awfully close to. Anyway. The logarithms shown in the table are convenient because the x values are powers of E. Most logarithm expressions, however, are best evaluated with the calculator. That's how I always do it. I don't think of the terms of those things. So, log of 2. Just pull out your calculator. Be sure you're in natural log mode when you do this, that you're not in some other base, that you're in the natural log. But ln, if you have that on the calculator, you're at that. And that's about 0.693. Okay? I mean, you just enter on the calculator. Huh? It doesn't matter what degree it is. Make sure you're. Yeah, right. If you got LNT. Yeah, right. And there's the log key. So don't ever use this one exactly. And you'll always be right. You don't need to be some of the older calculators, you had to tell it whether you're in what base you were in, LOG base, 10 or E, or 7 or 2 or whatever. But that one you have separate. But if you're using the LOG kit, you have to tell it what base. Log of 32, I'm just going to put them up here. You can punch them in your calculator. Log of something less than 1 is going to be a negative number. Okay? All right, now let's go back to here. Notice what logs do for you, though. So big numbers, 2's not that big, but that's a 0.7 approximately. 32 is much bigger number, but that's 3.4. If you did log of 320, you're still not going to be a very big number. Do log of 320. Is what? 5.7. Log of 3,200. 8 point or 80? 8, yeah. So you see you got pretty small numbers, even though your argument's getting huge, a log scales it down some. And that's advantageous when you're doing things astronomically, huge numbers. You can do a log scale, and in fact that's what, goodness, I always go blank on his name. Second?
Napier.
Not Napier. He's logarithms. The planetary motion. Doesn't say laws of planetary motion. Kepler. Johannes Kepler. He did log scales and came up with some really fascinating relationships. Okay, because he was doing of huge numbers. I mean, distance from Earth to Sun is 93 million miles, and that's one of the closer planets. The further ones out there are many times that. So your numbers were huge. He used logarithms and compared some things and really came up with some really neat characterizations. So logs do that for you. Yeah.
And so, what exactly is a logarithm again?
Okay.
What's that?
It has to do with the power of a number. Okay. Yeah.
Yeah, that's playing as well. And actually, like, how do we get from multiplication and division to logarithms from back then? Like, what was the current need for logarithms?
Well, is to reduce numbers in a sense. Like take a really big number, take a log of it, you have a very manageable number. Okay, so that was the reason Napier, I think, came up with it. Okay, now logarithms refer to the power of a number. So let's go back to this thing. E to the minus 3, if you take the log of e to the minus 3, you just get the minus 3. And so the logs are related to the powers of the numbers. So if you go up here to, if you're doing base 10, that would be probably easier to do and do the LOG of base 10. The log of 10 would be 1, because it's 10 to the first power. The log of 100 would be 2, because that's 10 to the second power. Log of 1,000 would be 3, because that would be its base. So that's what you're doing with logarithms. You're doing it on the scale of what the exponent would be. And that goes up much more slowly than the number does. Okay. Of course, down here, they get really big really fast, going in the negative direction. But that's all we seldom use too much down there. Okay. So that probably wasn't a satisfactory answer, but that is what logs do for you. Now, let's take the derivative of a natural logarithmic function. We defined it by an integral, so a derivative should do it in reverse, shouldn't it? Because it's an inverse operation. The derivative of the natural logarithm is given in this theorem, The first part of the theorem follows from the definition of the natural logarithm as an antiderivative, and the second part of the theorem is simply the chain rule version of the first part. Blah, blah, blah. So let u be some differentiable function of x, then the d by dx of log x is simply 1 over x. Okay? Well, we did the integral of 1 over x, that gave us log x, so if you do the derivative of log x, you should get 1 over x, and that's exactly what you get. Derivative of the natural logarithm is 1 over the argument. Now, if u was some function, rather than just a number, a differentiable function of x, the d by dx of this would be 1 over u, that's this part, times the derivative of u. That's the chain rule part. So it's u prime over u, which is an interesting concept in itself. The derivative of the natural log of u is the derivative of u over u, which comes straight from its definition. Okay. So the derivative of log of 2x would be, derivative of this would be 1 over 2x times derivative of 2x is 2. So it's 2 over 2x, which is 1 over x, which is rather bizarre because the derivative of x is also 1 over x. The derivative of 2x is 1 over x. It's strange but true. Okay? Because if you think about this, you could write this as log of 2 plus log of x, right? That's by the rule of logarithm. The log of a product is the sum of the logs. The log of 2 is a number. Just some number. And you take the derivative of a number, it's 0. And that gives you plus 1 over x. So sure enough. That is it. In other words, what you do to the logarithm is derivative, as long as you just multiply a number by it, the derivative, or the slope of the tangent line of that logarithm, is always the same. Seems bizarre, but it is true. Okay, how about this one? What would be the derivative? Oh, they don't write the answer to this one, so we can do it. What would be the first part of that?
X to the third over 3.
Wait. No. Derivative of log is just 1 over x squared plus 1. That's the first part. Derivative of the log. Now you do chain rule, derivative of the inner part. And what would that be? Don't integrate it. Derivative. Simple. Derivative of x squared. Say again? Not x. I mean, that's part of it, but that's not the whole thing. Say again? 2x, exactly. 2x. Here's what it is. Derivative of the inside over, no. Derivative of the inside over the inside, basically, is what you're doing every time. 1 over whatever the argument is, times derivative of that argument. That's it.
That's how you take the derivative of the log?
Yeah, that's what you do. Derivative of the log is 1 over whatever's inside, and then if the thing on the inside, you take the derivative of the chain rule. Yeah, that's what this was telling you. It's just u prime over u, okay? But I don't remember that. I just take the derivative of the log. I put whatever the argument is on the denominator and then take the derivative of that thing for the numerator. I'm doing exactly that, but I don't think of it in those terms. If you want to think of it in those terms, you can. The derivative of a log is always 1 over whatever follows the log, always. And if that thing is a function of x, then you take the derivative of it. So that goes in the numerator. Okay? Let's see if there's a C part. Oh.
There's a C part there. Let's get the answer first.
Yeah, they take one more step to get their answer than I did. Okay? 2x over, same answer. I just do 1 over the argument times the derivative of the argument. They wrote out u prime over u, which is fine. It's absolutely the same thing. What would that be then? Derivative of x log x. Second?
As opposed to doing the same thing that we just did with t,
Okay.
right? So we take
Well, first, this is a product rule. Okay? So how does a product rule go?
product is equal to the sum of itself.
Say that again?
I said the product is equal to the sum of itself, like of product.
Okay, now not the product of logs, the log of a product. That's not what I was saying. The derivative of a product. How do you do a product rule? Derivative of a product. Say again?
The first part times
Okay. Your first part, x, times derivative of the second part, which is,
1.
say again?
1.
1 over x. Right? Plus,
Do the second part times the derivative of the first part.
so that would be log x, because derivative of x is 1. Okay? So this would be x over x is 1 plus log x. Strange but true. Fairly simple answer. 1 plus log x. Let's see how they do it. Yeah, x times derivative of log x plus log x times derivative of x. Product rule. So it would be x times 1 over x plus log x times 1. That would be 1 plus log x. Right? Okay. Is there a D part? Yes, there is. How would you do that one? How would you do that? There's at least 2 ways you can approach it. How do you want to approach it? No, I'm sorry, I was thinking of a different expression. Basically, one way to do this.
We begin by multiplying the formula by 3.
Say that again.
Multiply ln x by 3.
Not multiplying it by 3. You're raising it to the third power. Multiplying it by itself, by itself, by itself. But you don't have to do that. This is just derivative. Okay. This is a power rule. Okay? So let u equal log x. Right? So this would be derivative with respect to I don't want to make it too complicated. Oops, I hit the wrong button. Sorry. Okay. Basically, this thing is not going back the way it's supposed. There it goes. Okay. Take derivative of this. That's a power rule. Okay. That would be 3 times log x squared. Okay. Right? Times 1 over x, derivative of the internal, right? So that would be, it's just chain rule. Okay, you could do a product rule with this. I hadn't thought of that. You could, but boy, that would be a pain in the neck to do, but you could do it. I hadn't thought of that, but yes, you could. But this is just simply derivative of a power is 3 times the argument raised to the second power, okay? Then times derivative of the internal part, that'd be 1 over x. So this will be 3 over x times log x squared. I don't know if that's how they write it. Let's see how they do. Delete my scratch. 3 times log x squared times derivative of log x. Chain rule. That'd be 3 times log x squared times 1 over x. Oh, that's how they leave it. Okay. Nothing more to it than that. I put the 3 over x in front. That's fine too. Or 3 log x squared over x. Any one of those ways would be perfectly fine. All right. Let's see if they do example 4. No, they don't do 4 or 5. Okay, let's do example 4. Differentiate this. F of x equal log of, whoops, I want to change it, but they didn't write it changed, so let me write it the way they did. Okay. Differentiate that. Now, before I do anything else, I always like to picture in my mind what's my domain here. You tell me what it is.
From 0 to infinity?
Actually, okay. What are you referring 0 to infinity?
What x can be?
Or x can be, okay. If you said x, actually x would be from -1 to infinity, but not counting -1, because -1 plus 1 is 0, okay? And you can't take the square root of 0, but you can't take the log of 0. So the -1 would be parentheses -1 to positive infinity because of that x plus 1 in there. Okay. That's not really important to what they're saying here. Well, it may be later, but we'll see. So how do we differentiate that?
First, rewrite it.
It's what?
Rewrite it.
Okay, how?
As the log of x plus 1 to the 1/2.
I like doing that. You're absolutely bought into what I was saying. So d by dx of f of x will be d by dx of this. Okay. Now what would that be then?
That'll be 1/2
Okay.
out front. And then x plus 1 equals the -1/2. I thought it was going to be times.
Okay, remember it's derivative of the derivative of the logarithm is 1 over whatever's in here, so that has to be down here, times the derivative of whatever's in there. So that is basically what you gave me first. So remember, you always have to put the argument of the logarithm in the denominator. That's where it goes. Okay. Now, if you take a look at that, that is simply 1 over 2 times 1 over x plus 1 to the first power. Because if you move this downstairs, that would be that by itself, and that would just be this. So, I don't know how you want to write it. 1 over 2 times x plus 1. To me, that's the simplest way to write it. The book probably will write it somewhat differently from that. If I can find, oh, there it is. No, yeah, that's exactly how they wrote it. So, all right, ready for example 5?
So what about the negative? How can you grab this plus 1 to the -1/2 x plus 1? That wouldn't be nothing negative because of the exponent is negative.
Okay. I know you're asking stuff about the negative exponent, is that right?
That doesn't affect the division.
Yeah, well, okay. What it does, okay, you can think of this two ways. Same base raised with different power. That would be this base, x plus 1 to the minus 1/2 minus a 1/2. And minus 1/2 minus 1/2 is minus 1. So it would be x plus 1 to the minus 1, which is 1 over x plus 1. Is that what you were saying? No.
Once you move it down to the bottom.
Yeah, what I did was move this downstairs and have it, and that makes it x plus 1 to the 1/2. So you have x plus 1 to the 1/2 from here, plus x times x plus 1 to the 1/2 from there. Well, that's the square root of this times the square root of that, which is that, x plus 1. Is that?
Yeah, that'll make most sense.
Okay. I'll have to remember that. No, I'm just kidding. Okay. All right, that was example 4, I'm sorry. How did I get 8? Okay. Let's do example 5. Can I erase this? Yay. Example 5. Differentiate this. F of x equal to, the log of x times x squared plus 1 squared over the square root of 2x cubed minus 1. We want to differentiate that function. Looks like a joy, doesn't it? Okay? Well, frankly, let's use your properties of logarithms to simplify that really complicated looking thing. So forget about derivative yet. Let's just simplify it first. What would that be?
Log of the slice part.
Yeah, x times x squared plus 1 squared. Minus, you're okay. Minus. The log of? Huh?
Minus the log of the bottom.
Okay. Well, I'm going to write that in exponential notation rather than radical. So 2x cubed minus 1 to the 1/2 power. Okay. Now, this part is a product, so let's write that as log x times plus the log of x squared plus 1 squared minus, and this time I'm going to do the 1/2 times the log of 2x cubed minus 1. Is that legal? Yeah. Okay. One more step we can do. This is the log of x plus 2 times the log of x squared plus 1, right? Power, thing, minus 1/2 the log of 2x cubed minus 1. Now, I can't do anything to simplify that any further with logarithm, our rules of logarithm. But now, this is the same as that. Now, let's take the derivative. This is your f of x. Now, let's do f prime of x. So, logarithm of 1 over x, logarithm of log x, derivative of log x is, I just told you the answer 3 times, 1 over x, okay, plus 2 times, what would that be? Derivative, yeah. 2x over x squared plus 1, right? Because the derivative of log is 1 over that times the derivative of that on top, that would be 2x, okay? I'll come back and clean that up in a minute. Minus 1/2, and what's the derivative of that? 6x in the numerator, and in the denominator, 2x cubed minus 1. What's that?
6x squared.
I can't hear you.
6x squared. You forgot the
Oh, square, yeah. I think I said it, but didn't write it. Okay, yeah. 6x squared. Okay? Now let's clean it up a little bit, and that would be 1 over x plus 4x over x squared plus 1 minus, and let's do the 2 will go into 6 3 times, 3x squared over 2x cubed minus 1. And I see no reason to write that in any other fashion. I don't see any reason for a least common denominator, though you could do it. Ew, I don't want to. Let's just leave it like that. Let's see what the book got. 1 over x plus 4x over x squared plus 1 minus 3x squared over 2x cubed minus 1. Good for them. Good for them that they left it in that form too. Okay. Okay, have we gone out of time?
Yes.
I was afraid of that. Okay. All right. Let's see. Where did we leave off here? We're going to do example 6 next time. But actually, before we do that, the on occasion here. So we actually do pick up a slide here. Pick up that slide right there. All right, homework exercises in this section. We almost finished 5.1. Do either 5 or 7. They're both at calcchat.com. I would do all of 9 through 12, but the odds 9 and 11 are at calcchat.com. Do any of the odds 13 through 17. They're all at CalcChat. 17's at CalcView. Do 19, it has 4 parts. It's at CalcChat and CalcView. Do any of the odds 21 to 29. They're all at CalcChat. 23's at CalcView. Do any of the odds 31 to 35. They're all at CalcChat. 31's at CalcView. Do 37. Do 39. Both of them are at CalcChat. Do any of the odds 43 to 49. No, I'm sorry, 43 to 65. They're all at CalcChat. 45's at CalcView. Do any of the odds, whoa, I think I got a little ahead of myself. Yeah, stop there. Stop at 65. We'll pick up the rest of those next time. Good deal. You too. We'll see you Wednesday.